How you guys doing? Hopefully pretty good. Let's do some more examples. Again, always keeping in mind not to use trig subs unless we have to. There is no part one. The integral of the square root of 4 minus x squared over x dx. Now this looks close to working out as a u substitution, but not quite. Let's try it together. I don't think it'll work. But let's try it together because I really want to push this idea. If u is 4 minus x squared, then du is negative 2x dx, which we don't have. So this is one of those situations where it's easier to solve for dx. And if we do that, I'm going to keep this in red. We might erase it all, but I just want to really reaffirm that I want you to kind of look at this. If we have this, we get, this just becomes the square root of u. I'll have an x down here. And this becomes negative 1 over 2x du. The negative a half comes out in front. Square root of u over x squared du. Maybe this is working, maybe not. What is x squared? X squared is 4 minus u. This is a negative 1/2 integral square root of u over 4 minus u du. I don't think this is any better. I don't think this is any better. You can almost do another substitution, but it doesn't quite work out. Could we use integration by parts on this? Nah, not really. Yeah, it's doomed. All right, we're going to have to use a trig sub. But it's important, again, what did that take? A minute? 2 minutes? But it can potentially save a lot of time. So I really want to encourage all of you guys to think about something like that. Okay, so which one do we use? I'm not going to scroll back to 5,000 pages, but remember those 3 identities. That'll tell us what trig sub to use. Okay, 1 minus sine squared is cosine squared. Let's use that one. Let x be 2 cosine of theta. Why did I choose that? So x squared is 4 cosine squared. All right. And then dx, well now, sorry. Cosine works. There's nothing wrong with cosine, but I'm trying to be consistent with everybody. We're going to use sines here. Nothing wrong with cosine. It'll work. The dx is 2 cosine of theta d theta. This becomes the integral of 4 minus 4 sine squared of theta over x, which is 2 sine of theta, times dx, which is 2 cosine of theta d theta. The 2's cancel. I'm going to go off to the side and evaluate this. This is the square root of 4 times 1 minus sine squared of theta. That's 2 times the square root of cosine squared of theta. That's 2 times the absolute value of cosine of theta. And again, we know theta is from negative pi over 2 to pi over 2. So in that domain, it's 2 cosine of theta. So the whole square root is just 2 cosine of theta. You do that off to the side and are neat and clean with your work, that can be a good strategy. We're left with 2 cosine of theta over sine of theta times, well, there's another cosine of theta in the top. We'll write that as cosine squared. Don't write this as cotangent. Cosine over sine is cotangent. Don't do that. This is a u substitution. Wait. Oh, maybe it's not. I thought it was a u substitution. Not yet. It's not a u substitution yet. But one of the things that we could do is put everything in terms of sine. If we put everything in terms of sine, I think it works out pretty nicely. Wondering, is there another way? They're another nice thing because I don't think a U sub will work. This is cotangent times cosine. Pretty sure that's a bad idea. Yeah, let's put things in terms of sine. That'll be 2. We can bring that in front. Cosine squared is 1 minus sine squared of theta. And now we can just split up the fraction. So we'll get 2 times the integral. 1 over sine of theta is cosecant minus sine squared over sine of theta, which is sine of theta. And again, we could evaluate the antiderivative of cosecant using the topics that we've already covered, or we could just use that formula. I believe it's negative, just like the negative one. It's like the negative version of secant. So it'll be like negative natural log of absolute cosecant x plus cotangent of x or something. And then the antiderivative of sine is negative cosine. I'm going to double check that one real quick. Antiderivative of cosecant is negative natural log of cosecant plus cotangent. Great. That's that relationship with a lot of trig and calculus for something, and it's like cofunction. So secant and cosecant, it's going to be the same relationship with tangent and cotangent. All right. So what we got here, we can just keep simplifying. We could do maybe one more step. Oh, these are thetas. The formula that I was thinking of was x's, but they are still thetas. And now we remember that x was equal to 2 times sine. So that tells us that sine of theta is x over 2. We need to know what cosecant, well, cosecant, oh, we already know that, right? Cosecant is the reciprocal of sine. This will be 2 over x. But we need cosine and cotangent. Let's draw a reference triangle. So we either know we're in the first, all right, so even if we're in the 4th quadrant, it's actually okay, because sine will already be negative anywhere. Anyway, so this is just sine, sine over cosine. And that's probably a good way to writing this. So it's sine over cosine. Or we can calculate cotangent directly. So sine of theta is x over 2, opposite over hypotenuse. Pythagorean theorem says this is what this will be. So the cotangent is going to be 1 over tangent. So it's the reciprocal of opposite over adjacent. It's adjacent over opposite. Yeah, and if x is negative, we're still negative, and x is positive, we're still positive, just like we wanted. So this is going to be 2 times negative natural log of the absolute value of 2 over x plus cotangent. And then cosine is going to be adjacent over hypotenuse. So that'll be like so. And then we can distribute the 2 and be done. All right. We get negative 2 natural log. Oh, we can combine these fractions. You actually might be able to simplify this by rationalizing the numerator, but I don't think so. And then should get something like this as our final answer. And let's check it. Okay. Let's check it. How do I want to check this actually? Could check it with the book. This is example something. This is example 3.22. Wait, is it? Is that what we did? 2 ln 2 over x minus, oh, Did I have a plus in my formula? Cosecant plus cotangent. Why do they have a minus? Wait, what am I looking at? 3.22. 2 ln of 2 minus square root of 4 minus x squared plus square root of 4 minus x squared. So they have a minus here. And but I have a negative here. It might just be a different formula. They might be equivalent. I don't see why they'd be equivalent though. Antiderivative of cosecant. Oh, they're just using a different formula for the antiderivative of cosecant. They use cosecant. I think they're equivalent. I'll check that out later, but should be probably maybe equivalent. We'll look at that at the end of the video. All right, next problem. Example 5. Find the arc length. Yeah, we love arc length. Chapter 2 stuff. Of y equals x squared over 0 to 1/2. So remember that the arc length is the integral from a to b of the square root of 1 plus the derivative, the first derivative, not the second derivative, squared dx. So our derivative here is just 2x. This is easy. From 0 to 1/2, 1 plus 2x being squared is 4x squared. Oh, it's a trig integral. This is not a circle. This is a hyperbola again. We're gonna have to use a tangent sub. Don't worry, it's not secant. That's the next video. Next video is the return of secant. Okay. So again, 1 plus tangent squared is secant squared. That tells us that we want to do a trig sub here. We want 4x squared to be tangent squared. So what is x going to be? Well, that means x squared is going to be 1/4 tangent squared. So x has to be 1/2 tangent. And again, these parts are optional, but I think they're really helpful to get where we want to go. We want the integrand to be 1 plus tangent squared here. Okay, so that tells us that dx will be 1/2 secant squared of theta d theta. And now we have most of what we need. Let's give ourselves some more room. And we're going to need the limits of integration. Let's worry about those in a moment. Square root of 1 plus tangent squared of theta. Dx, it's 1/2 secant squared of theta d theta. All that's left is, well, if x is equal to 0, what is theta? 0 is 1/2 tangent of theta. So if theta is 0, we're good to go. The other one, when is 1/2 equal to 1/2 tangent of theta? Well, that's when tangent of theta is 1. When is tangent of theta 1? At pi over 4. Oh, this one's nicer. Not too bad. Integral from 0 to pi over 4. This just becomes the square root of secant squared. The 1/2 comes out in front. We still have a secant squared. They really brought this secant cubed integral back again. All right. I guess it's because it's the same. All right. Whatever. Okay, so on this interval, right? When theta is between 0 and pi over 4. That's the first quadrant. Secant's going to be positive in the first quadrant because cosine's positive in the first quadrant. So the square root and the squared cancel, and we're just going to get secant cubed again. 0 to pi over 4 of secant times secant squared, which is secant cubed. And just like before, again, I'm not going to, on quizzes or exams, force you to do this within another within a 3.3 problem. If I do, I'll give you the formula. But you should be able to evaluate this integral with integration by parts. Okay? Where u is going to be secant, and dv will be secant squared. And then you have to do it twice and then move one of the integrals over. I just don't want to spend the time doing that right now. I'm just going to use that formula that I found earlier, that it is going to be, where'd it go? Secant cubed, going to be 1/2 secant tangent plus 1/2 natural log absolute secant plus tangent. Again, that 1/2 comes from dividing over the 2 when you do integration by parts twice. And then you just plug in pi over 4 and 1 and we're done. Boring, I know. Secant is 1 over cosine of pi over 4. Then we have tangent of pi over 4 plus 1/2 natural log of, again, 1 over cosine of pi over 4 plus tangent of pi over 4. And then we subtract, we plug in 0. Secant of 0 is 1, tangent of 0 is 0. Secant of 0 is 1, tangent of 0 is 0. The natural log of 1 is equal to 0. So this whole thing is 0. Cosine of pi over 4. Cosine of pi over 4 is 1 over root 2. So 1 over that, or the secant, is just root 2. This is 1/2 times 1/2 times root 2 times its tangent. Tangent of pi over 4 is 1. Plus 1/2 natural log of, again, square root of 2 plus tangent, which is 1. We're almost done. No problem. This becomes root 2 over 2 plus 1/2 natural log. This doesn't simplify, but we don't need the absolute values. We'll get root 2 over 4 plus 1/4 natural log of square root of 2 plus 1 is our final answer. I feel pretty confident about that. Check it out. Check our answer. Is the integral from 0 to 1/2 of the square root of 1 plus 4x squared dx, is that arc length equal to the square root of 2 divided by 4 plus 1/4 times the natural log of the square root of 2 plus 1? There you go. If you didn't have Desmos, you could get an approximate answer with the Pythagorean theorem as well. Okay, so that's the main end of the video. I'm going to spend a little time at the end. Again, you don't have to watch this part. I want to spend a little time at the end, though, looking at this guy over here and verifying whether this is indeed equal to what the book has, which really just matters. Is this other part really about, is this other part equal to the other thing? So this is our answer here. Right? And if I just move this real quick, the end, so everything's where it needs to be. And the book has their answer on this one to be 2 ln 2 over x. I don't see how these would be the same. So really, it's just a question of, are those natural logs the same? And again, I just really don't see how they are. But let's just double check. I'm going to double check graphically first. -2 ln of the absolute value of 2 plus square root of 4 minus x squared all over x. Oh, it's all over x. Dang it. And the book has 2 times natural log of the absolute value of 2 over x minus square root of 4 minus x squared over x. Oh, it doesn't like this. Oh, huh. They're mostly the same. It actually doesn't like the book's one as much as it likes mine. That's interesting. Or maybe it's just oh no, it's because of approximations and stuff like that. Okay, they are the same. Great. Just wanted to double check that, make sure I wasn't lying to you guys. Let me know if you have any questions, and best of luck.